Hello class, welcome to this video on lesson 10.1 practice. So let's go ahead and take a look at these questions. So what critical value t star should be used for a confidence interval for the population mean in each of the following situations? All right, so we have our t table at the end of this packet, right? So of questions, so we can take a look at that. So we can use this t distribution table for these questions. Okay, so all right, so it says 95% confidence interval based on n equals 10 randomly selected observations. Okay, so 95%. So remember, the area is going to be 0.95 divided by 2, which is 0.05 divided by 2. So the area that we're looking for is 0.025. So this is the area in the tail. And then the df, the degrees of freedom, is 10 minus 1 or 9 observations, or the df is 9. All right, so we're going to look up the t critical for that. So 0.025 and then df equals 9. All right, so we got 0.025 for the tail probability, and then we got a df of 9. So that means it's 2.262. All right, so there's our critical value. All right, and then again, you can also use this doing with the calculator. So 99% confidence interval for 20. So we get, so the area equals 1 minus 0.99 divided by 2, which is 0.01 divided by 2, so 0.005 for the area, and the df is 19. So we look for that, 0.005 and then 19. 0.005, and then you got a df of 19 right there. So it looks like 2.861. Okay. All right, so then we got a 90% confidence interval. So we got 1 minus 0.90 divided by 2, which is 0.10 divided by 2, or 0.05. And so our df is 77 minus 1, or 76. And so we want to choose one that is smaller than that, because the table doesn't give us 76. I think it gives us 70 and 80. And so we want to use df equals 70. We want to be conservative in how many degrees of freedom that we give. And so so we're going to be using that, and then 0.05. So let's go to the table. 0.05, and then we have, so actually they give us 60 or 80, so they don't even have 70. So so we got 0.05, and we're going to have to use 60 because that's the smallest, the biggest value that is smaller than it. Right, so 60, and then we got 1.671 for 0.05. Okay, so we're gonna use 60, 1.671. So let me double check that. All right. 1.671, and that's 60. And now we're going to show you how to do this on a calculator, because we had to use the table and it wasn't the greatest, right? Because, you know, we had to go for a df of 60. So let's do a calculator value to see what that ends up looking like. Okay. All right, so we're in the calculator, and let's see how this looks like. Okay, so we're going to do second, and then we're going to go vars, second vars, and then go down to inverse t, number 4. Then we're going to go to area is 0.05. We're going to go down to df, which was 76. All right, so we get negative 1.665. All right, so we get about 1.665 on the calculator, which is pretty close to the 1.671, right? All right. So you can use either one of these values depending on if you use calculator or table. All right, so number 2, what critical value t? So it's another critical value question. So again, we don't have to do the area all over again. We know that the area based off of what we just calculated for 90% is 0.05. And we know that DF is 11, so we can calculate the critical value for that. Okay, so we got 11 and then 0.05. So 1.796, 0.05. Okay, 1.796. Now here we got 95%, so the area is 0.025, and the DF is 30 minus 1, which is 29. We got 0.025 and 29. 0.025, 29. So 2.045. Okay, and then 99% area is equal to 0.005, and then you got your DF is 57, random sample size of size 58. And so we can't use 60, so we're gonna end up using, so what is it, 57 and then 0.005. Okay. We get 0.005. And then we want to use 50 because that's just the biggest number that is smaller. Okay, so 2.678. 2.678. Oh, all right, and we'll see what that looks like on the calculator. Okay, so let me change these values here. 0.005, and it was 57, I believe. All right, so negative 2.66. All right, so then on the calculator, 2.66. It should be 2.665, all right? So it's pretty close to that. All right, so number 3, velvet leaf is a particularly annoying weed in cornfields. It produces lots of seeds, and the seeds wait in the soil for years until conditions are right for sprouting. How many seeds do velvet leaf plants produce? The histogram shows accounts from a random sample of 28 plants that came up in the cornfield where no herbicide was used. Determine if the normal large sample condition is met in this context. All right, so we know that n is equal to 28, which is less than 30. And so therefore, by the normal large sample condition, we must draw the graph. We must provide a graph to determine if there's enough evidence to say if there's any outliers or if there's strong. We want to see if there's outliers, and we want to see if there's strong skewness, all right? That's what we want to do. So it looks like this is strongly skewed to the right? So there are outliers in the data. So we can say that the sample size is small and there are outliers in the data. So that automatically eliminates this. Okay, so we're going to say the conditions are not met. Okay, because n is less than 30 and there are outliers in the data. So cannot assume population is approximately normal. And therefore we do not meet the condition, so we would not be able to do a one sample confidence interval for T, or one sample confidence interval for mu. So Judy is interested in the reading level of a medical journal. It says she records the length of a random sample of 100 words. The histogram displays the distribution of word length for her sample. Determine if the normal large sample condition is met. Okay, so in this case, we have that she records the length of a random sample of 100 words. So in this case, well, it is met. We don't even need the graph. It doesn't matter that this is skewed right, even if it had outliers or anything like that, because the sample size is large enough, then that's going to be enough for what we need, okay? So the conditions are met since n equals 100 is greater than or equal to 30, okay? Regardless of the shape in this case. All right, number 5. Determine if the conditions are met for constructing a confidence interval for the population mean in each of the following settings. So how much time do students at your school spend on the internet? You collect data from 32 members of your AP Statistics class and calculate the mean amount of time that these students spend on the internet yesterday. All right, so let's check the random condition. So is that random condition met? Well, it says it cannot be met because in this case, you are selecting students, you collecting data from your AP Statistics class, right? So it's not a random sample of students. It's actually a convenience sample, right? But let's check the other one. So 10%. We can assume that 32 is less than 10% of all students at the school, or at the school. And then we can let's check the normal large sample condition. In this case, this is met because we had 32 students, which is greater than or equal to 30. But this is not met. All right, so part B, is the real estate market heading up or heating up? To estimate the mean sales price, a realtor in a large city randomly selected 100 home sales from the previous 6 months in her city. These sales prices are displayed in the box plot. All right. So now let's look at the conditions. So random. So it says they randomly selected 100 home sales from the previous 6 months. Okay, so yes, we can say that it is, right? So we can say random sample of 100 home sales from previous 6 months in the city. All right, so then let's look at the 10% condition. So we could say that 100 is less than 10% of all homes sold in the past 6 months in the city. All right, and then we got the large sample condition, the normal / large sample condition. So in this case, we can say, well, we have 100 homes. It doesn't really matter that we have outliers there because we have a large enough sample size. So n equals 100 is greater than or equal to 30. So even though there are outliers, it's still met because the sample size is large. All right. So it doesn't matter. All right, 6. Breastfeeding mothers secrete calcium into their milk. Some of the calcium may come from their bones, so mothers may lose bone mineral. Researchers measured the percent change in bone mineral content, or BMC, of the spines of 47 randomly selected mothers during 3 months of breastfeeding. Okay, the mean change in bone mineral content was negative 3.587%, and the standard deviation was 2.506%. Construct and interpret a 99% confidence interval to estimate the mean percent change in BMC in the population of breastfeeding mothers. Okay. All right, so let's go do all the steps. So we got the state, plan, do, right, all that stuff. So let's do the state. So the state is, well, what are we doing? We're doing a 99% confidence interval for what? For mu. Right? the mean percent of change, right? So so mu equals the true mean percent, or yeah, mean percent change in BMC for breastfeeding mothers, right? All right, so that's the state. Now we're going to do the plan. So we are doing a one sample T interval. All right, so one sample T interval for mu. And then, well, let's check the conditions. Okay, so let's check the random condition. All right, so yes, that's satisfied. Mothers were randomly selected. So I'm going to put 47 mothers were randomly selected. All right, and then let's do the 10%. We're going to assume 47 is less than 10% of all breastfeeding mothers. Then we got the normal or large sample condition. Right, in this case we have n is equal to 47, which is greater than or equal to 30. So that's met automatically. All right, so let's do the do stage, right? All right, so now let's go ahead and calculate. So we need to find the degree of freedom. So we know that df is equal to 47, I'm sorry. 47 minus 1, which is 46. So remember, on the table, we're going to use df equals 40 for the table. And if we use 40 for the table, then we get a t star. So let's see, we got 46. Oh, we can do the area. So the area was 1 minus 0.99 divided by 2. So that's 0.01. So that's 0.005. So 0.005, and then we're going to use 40 from the table, okay? Okay, so 40, and then 0.005 right here. Okay, so 2.704. We got 2.704. All right, I'm going to put here table A. Or table B. Table B is the t distribution table. Okay, so now let's go ahead and calculate the confidence interval. So then the confidence interval is x bar plus or minus t star sx over square root of n. So we have x bar, which they said that the average was negative 3.587%, plus or minus the t star times the standard deviation was 2.506%. Over the square root of 47. All right, and if we do this, we get about, this is just roughly, negative 4.569, negative 2.605%. All right, so there's my confidence interval. And then we got to conclude. All right, so now we are 99% confident that the interval from negative 4.569 to negative 2.605 captures mu equals the true mean percent change in BMC for breastfeeding mothers. Okay. All right, so now let's look at the question here. It says, based on your interval from part A, do these data give convincing evidence that nursing mothers lose bone mineral on average? Explain your answer. So yeah, notice that their 0 is not contained in our interval, right? So it looks like we have evidence and significant evidence that there's going to be that of bone loss. You know, both of these numbers are negative. All the plausible values from our interval are negative, right? So therefore, there is convincing evidence of bone loss, right? All plausible values in the confidence interval are negative, which means bone loss. So the data gives convincing evidence. All right, so now let's look at the last question here. Should be the last question, or there's going to be probably another one here. All right, so Ann and Tori wanted to estimate the average weight of an Oreo cookie to determine if it was less than advertised, 34 grams for 3 cookies. They selected at random a random sample of 36 cookies and found the weight of each cookie in grams. The mean weight was X bar, this should say X bar, equals 11.3921 grams, with a standard deviation of SX equals 0.0817 grams. Construct and interpret a 90% confidence interval for the true mean weight of an Oreo cookie. Okay, so let's do the state, right? All right, so we're doing a 90% confidence interval. Or yeah, let me be more specific. Yeah, confidence interval for mu equals the true, let me see, the true mean weight of an Oreo cookie. All right, so then we got plan. So we're doing a 1 sample t interval for mu, and then our conditions. So random condition. Cookies randomly selected. All right, 10%. 36 is less than 10% of all Oreo cookies. All right, and then we got the normal / large sample condition. All right, so then we can say n is equal to 36 is greater than or equal to 30. So that's good, so check. All right, so now we're gonna do the do stage. So let's go ahead and do the df. So df is 36 minus 1, which is 35. Now if you go to the t table, it goes from 30, it jumps from 30 to 40. So we're gonna use df is equal to 30. So table B, okay? And then we are going to, you can use a calculator. In that case, you would use 35 for the df, but here we're using a table. So if we use df is equal to 30, then we can go ahead and also let's do the area. So the area is 1 minus 0.90 divided by 2, which is 0.05. And then so we can figure out what our the critical value for t is. All right, so we got df is 30, and then we got area is 0.05. Okay, so 0.05 and then 30. So it's 1.697. All right, and in that case, we can do the formula. All right, so X bar, it says the mean of the random sample, 11.3921 grams. 11.3921 plus or minus, and then you got your standard deviation, 0.0817. Oh, I forgot to do the t. So the t is 1.697. 0.0817. Over square root of 36 cookies. All right, and then if we calculate that, we get around 11.369, 11.4152, 11.3690, I guess I should say. All right, and again, let me show you show you a technology to calculate that as well, just so that you know. So DF is 35 and area is 0.05. All right, so then what we're going to do is we're going to go to stat and we're going to go to tests. We're going to go to one. Okay, so we're going to go to, sorry about that. We're going to go to T interval right here, number 8. Then we're not going to use data. Because we're not typing in the data. We're going to use stats. Okay, so we're going to go to stats, and then we're going to input the stuff that they told us. So the X bar, that was 11.3921. Then you got SX, that was the standard deviation 0.0817. Then you had N is equal to 36 cookies you had. The confidence level was 90%, so let's change that to 9.90. And then we can calculate that. And you can see 11.369 and 11.415. That is pretty close to what we got earlier. Okay, so that's what we got with technology, which is very close to what we got by hand. So now let's go ahead and interpret the confidence level there. Okay, so how do we interpret the confidence level? So what that means is that, oh, actually, I didn't even finish the question. So let's conclude. Sorry about that. All right, so conclude. So we're interpreting the confidence interval, not the confidence level, the confidence interval. There's a difference, right? Okay. Okay, so we're going to say we are 90% confident that the interval from 11.369 oh goodness, let me see. Hello. All right, so we are 90% confidence that the interval from 11.3690 to 11.415 to captures mu equals the true mean weight for all Oreo cookies. All right, so now let's look at, so that's interpreting the confidence interval, right? So now we're going to interpret the confidence level. Okay, so that's different. You want to know the difference between those two things. So the confidence level, which the confidence level was 90%, right? So we want to interpret what the 90% means in the confidence level. So what it means essentially is that if we were to do many random samples of 36 Oreo cookies, right? Take many random samples of size 36 from the population of Oreo cookies, and then we were to construct a 90% confidence interval using each of the samples of the 36 cookies, then 90%, approximately 90% of those intervals would have or capture the true mean weight. Okay, so if we were to select many, I'm just going to say many, but many random samples of size 36 from population of all Oreo cookies and construct a 90% confidence interval using each sample about 90% of the intervals would capture the true mean weight of an Oreo cookie. Okay, so that's the difference between interpreting the confidence level versus interpreting the confidence interval. All right, so we got one last question. Melissa and Madeline love pepperoni pizza, but sometimes they are disappointed with the small number of pepperonis on their pizza. So to investigate, they went to their favorite pizza restaurant at 10 random times during the week and ordered a large pepperoni pizza. Here are the number of pepperonis on each pizza. Okay, so they got the number of pepperonis for 10 pizzas, so 10 random times. So construct and interpret a 95% confidence interval for the true mean number of pepperonis on a large pizza at this restaurant. Okay, so let's go ahead and do this then. So first off, we want to make sure we follow the process, right? So state. Okay, so we are going to state what we're going to do it. So in this case, we are doing a 95% confidence interval for mu equals the true mean number of pepperonis on a large pizza at this restaurant. All right, and then let's go ahead and plan. So we're doing a 1 sample t interval for mu. All right, so let's check the conditions. All right, so random condition. Pizzas were randomly selected. Is that true? Let's see. It says 10 random times. So yeah, pizzas were randomly selected. Okay. All right, let me go ahead and write it down here. Okay, so pizzas. All right, we're randomly selected. Now let's look at the 10% condition, see if that's true. Okay. Okay, so we got 10 pizzas, right? So we're gonna say that 10 is less than 10% of all pepperoni pizzas. Made at this restaurant. All right, and then the last condition, normal/large sample condition. So what we need to do, we know that the sample size is 10, which is less than 30, right? So that means that we need to draw a graph, a visual representation of this, either a histogram or a stem plot or dot plot or something like that. Dot plot is usually a really easy way to do it. So I would do a dot plot just because it's simple, okay? So, so we're going to say, okay, we got the number of pepperonis. And okay, so we got something in the 20s, 30s, and 40s. So let's just say, okay, let's just start at around 20s or 25, and then we'll go by like fives or something like that. Okay, however way you want to do it. And then we got 25 pepperoni, so that's one dot there. Let me just cross them out as I go. We got 32, so two 32s. So that's 1, 2. That's for 32. We got 34. All right, and then we got 36. We got 37. We got two 36s. We got a 37. Then it looks like we got 40s. So we got 46, 47, and 49. Okay, so now we got our dot plots, we got our visual representation. So now we can look. It says there doesn't look to be any strong skewness here, so that's good. We do have some gaps, but most of the data look pretty close together. There doesn't seem to be any strong outliers. Now you can calculate the outliers, but it's not necessary. We can kind of tell. All right, so dot plot doesn't show any outliers or strong skewness. Okay, you can see that because you have a big cluster there, and then you have a cluster there. They're pretty close. It's not too bad. So I would say we can continue with the test. It doesn't show any outliers or strong skewness or any apparent outliers. Or strong skewness, so then we can go ahead and proceed with the test and then do not the test, but in this case, the confidence interval. Now we need to do the data. So we need to know what our X bar is. We need to know what our SX is on the sample standard deviation. We know that it's 10 numbers. And so we can calculate the DF as well. So we can do that. Okay, so that means the DF is 10 minus 1, which is 9. And then, so we let us calculate these. Now we're going to need to plug these numbers into the calculator. Okay, so that's what we're going to do. Plug them into the calculator and then calculate the X bar and all that. All right, so we're going to need to calculate those numbers. So let's go ahead and calculate them. So we're going to hit Stat, Edit, and let's go ahead and type those numbers. So we got, let's see, 47 pepperonis, followed by 36. Then there's 25, 37, 46, 36 pepperonis, 49, 32, 32, and 34. So that's 10 pizzas there. So now we're going to hit Stat, and then we're going to go to Calculate, and we're going to go to 1var stats. List L1, that's fine. And then we can calculate. So we get our X bar, so that's 37.4. And we got our SX, which is 7.66. All right, so I showed you how to calculate them on the calculator. So now we can go ahead and put those here. So we got 37.4. We got this is 7.662. So we are ready. We're almost ready. So we need to calculate the T star, the T critical value. So the T critical value, we can get this from the table. So DF is 9, and then oh yeah, let's do the area. So I forgot to do the area. So we are doing a 95% confidence interval. So we got 1 minus 0.95 divided by 2, which is 0.025. So 0.025 and then df is 9. 0.025, df is 9. So that's 2.262. All right, so now we can calculate it. So we get x bar plus or minus t star s over square root of n. All right, so we got our x bar 37.4 plus or minus 7.6, or the t star is 2.262 times 7.662 divided by square root of 10, and we'll give you approximately what that is. So you get about 31.919. You get 42.881 approximately. All right. If you use technology, you get a very similar result. All right. So then we can go ahead and conclude. We are 95%. We are 95% confident at the interval from 31.919 to 42.881 captures mu equals the true mean number of pepperonis. On a large pizza at this restaurant. All right, that's going to do it for the video, guys. I hope you found this informative. And as usual, I'll see you in the next one.